This module will cover the pack and warp analysis. The goal of this module will be to learn the procedures for running a pack and warp analysis. Why do this? It's important to capture the shrinkage, warpage, as well as the sink marks in your part. So the influence in part quality. The packing phase is a large section of the injection molding cycle, as you can see from the image below. Part quality, and when we say that we mean shrinkage and warpage, is affected by the molding process history. So before we go any further, we should first clarify two key concepts by defining shrinkage and warpage. Shrinkage is simply defined as an in-plane change in shape, whereas warpage is an out-of-plane change in shape. There are several factors that can affect shrinkage. They are volumetric shrinkage, your cooling rates, orientation due to filling, your mold restraint, as well as temperature differences through the thickness of your part. Some of the contributors to warp would be part design, so our wall thickness or variations in it, part stiffness or its shape. For mold design, we can look at gate locations, runner and gate design, the cooling system configuration, or the ejection system even. Processing conditions would be mold temperature, melt temperature, injection time, and packing pressure. As for the material, that would be the molecular structure. Is it crystalline material or an amorphous material? They can both behave differently from one another. And does that material have fillers or not? When we look at for causes for warp, we're looking at three main components. That would be differential cooling, differential shrinkage, and orientation effects. We'll take a closer look at these three in the next couple slides. Differential cooling is typically defined by a shrinkage variation through the thickness of your part. This can be caused by uneven temperatures across the mold, so maybe your core versus your cavity are different. Variations in the wall thickness, or even thermal properties within your mold. We covered some of these topics in more detail in the Moldflow Design Principles module, so please feel free to reference that if you have not and would like additional information. Differential shrinkage is usually defined as shrinkage variation across your part, so basically from one end of the part to another, or in different regions. This is typically caused by wall thickness variations, your gate location, the cooling layout, or even some of your process settings. So to decrease differential shrinkage, we can typically play with a few different pack profiles here. This slide illustrates a few examples of what you might be able to try if you're having issues with differential shrinkage in your part. So to adjust the end region, which would be the last place to fill, you'll adjust the constant pressure duration. So we'll lengthen the amount of time that we see on that plateau. Shorten it to raise volumetric shrinkage, or we'll lengthen it to lower the volumetric shrinkage in that area. To adjust the gate region, we'd basically change the rate of pressure decay. So the slower the decay, the lower the volumetric shrinkage. The faster, the higher the volumetric shrinkage. And then to adjust the mid-region, which would be between the gate and last place to fill, we could put a step in that slope. If we increase it, that'll lower our volumetric shrinkage. If we decrease it, that can raise our volumetric shrinkage. You might say, why do I want to raise my volumetric shrinkage? Well, maybe you have some areas around the gate that you're overpacking, and that'll cause areas quite a bit of differential shrinkage because you've got areas that are overpacked and maybe areas that are significantly underpacked. So utilizing a pressure profile like this for your pack pressures could help you in those areas that are overpacked and therefore decrease the amount of differential shrinkage from region to region in your part. And our final component, orientation effects, is defined by different amounts of shrinkage parallel and perpendicular to the flow direction. This is commonly caused by orientation, whether it's molecular or fiber, the gate positions, the cooling layout, and even the process settings. In regards to orientation effects, your result will largely be impacted by whether the material is filled or unfilled. So filled materials shrink less along the direction in which the fibers are aligned. So that would be the flow direction. Compared to the transverse to that flow direction, or perpendicular to it, they would shrink more. For unfilled materials, the shrinkage is typically the opposite. So they'll shrink more parallel to the flow direction rather than perpendicular. This is because you have these molecular chains that are aligned and they just want to return to a stress-free state. So, being that they're stretched out further and more in the flow direction, they want to shrink back more in the flow direction. And unfilled materials don't have any fibers present to resist that, so they're allowed to do so. This is very important to keep in mind. So fill, pack, and warp analysis, that essentially adds the pack and warp onto the fill analysis that we took a look at earlier. So this extends the capabilities to basically simulate the packing phase of our injection molding process. And that way we can predict and minimize undesirable part shrinkage. The warpage portion will advise us if there are any indicators on if the part is likely to warp or deform beyond our acceptable values or tolerances. Both of these basically enable you to evaluate your mold design, your material, and your process conditions to obtain good quality parts. To run a fill, pack, warp analysis, you'll go in your analysis option and basically check fill, pack, and then check warp. Please be advised that this does require a Moldflow Advisor Ultimate license. If you do not have this license, this option will be grayed out, and if you click on it, it should inform you of that in the analysis information box at the bottom. Once you enable the fill, pack option in your analysis wizard, you'll see this tab available. In here, you'll be able to specify your packing profile options. So, you can specify your pack by either a percentage of the fill pressure versus time, or as an absolute packing pressure versus time. Once you specify these values in that chart or that table, you have the option to plot them so you can see a visual representation of what you're trying to accomplish. Just to confirm, which term defines the in-plane change in shape for a given geometry? Which term defines the out-of-plane change in shape for a given geometry? What are the three main causes for warp? Filled materials shrink greater in which direction? Now we'll take a closer look at interpreting some of our packing results. Like most of the other analysis sequences, once your pack analysis completes, you'll be presented with this summary tab. Within here you can see a nice snapshot of what's going on. So you can see the max clamp force during the cycle, the maximum wall shear stress, the total part weight, the cooling time, and even the actual packing profile. Our pack analysis will give us this result, the volumetric shrinkage at ejection. What this is giving us is the indication of how the volume is reduced between the original model's volume and our molded part at room temperature, which is 25 degrees Celsius. Basically shows us how much it shrinks in volume in a percentage. So when we're looking at this, we need to really determine, is our volumetric shrinkage acceptable? So some things you need to consider are the values in the expected range for the material? Some materials are naturally shrink more. Are the shrinkage values uniform throughout the part? Are there localized areas of high shrinkage in the part? Are there negative volumetric shrinkage values in the part, which could indicate overpacking? Solving some of these problems, you can do these by maybe considering some of those pack profile tricks that we showed you in a couple slides prior. Because really, what we're trying to do is get a uniform shrinkage throughout the part, and some of those pack profile tricks could help there. Which additional result is produced by running a pack analysis? Now we'll take a look at interpreting some results from our warp analysis. Some things to keep in mind when running a warp analysis is that you can see there's a checkbox in your analysis wizard, but it will not be available unless you run a packing analysis. So you have to have these both checked if you'd like to run a warp. The warp calculations are based off PVT data as well as the mechanical properties for the material you're using. The effects of fiber are also considered in our warpage calculations. If you're running a warpage analysis on a 3D part, you may notice this aggregation option in your analysis wizard. What this does is to help reduce analysis time and memory usage through an averaging method. You can disable this to give you more accurate results, but beware, this will increase your analysis time if you disable it. Disabling it will also give you the option to have access to 3 additional plots. That would be the differential shrinkage, the differential cooling, and orientation effects plots. This slide will show you a quick example of how filler can affect your warpage results. So on the left, we have a filled material. On the right, we have an unfilled material. So those top images have the overall deflection result for those. And the bottom is showing us the individual contribution that actual orientation effects has on it. You can see that we are picking up a difference with this part, even though it is the same geometry and process settings and gate location. So we do consider this. Now when we get your warpage results, they're a little different from the results that we've seen in previous modules. Previous modules, you look at the result and it is what it is. The warpage results, typically you need to use what we call an anchor plane. You need to specify a nominal maximum deflection, which is basically your tolerance. And there's also a best fit option for viewing your results. So, there are several tools that you can use to interpret your results. So the first one we'll look at is the anchor plane. This allows you to define 3 points on your model that define the anchor plane used to calculate your deflection. The first point defines your origin. The second point constrains the movement of your part in the x direction. And the third point defines the x and y plane. So, using this tool does not alter the results on your part. It's simply a way of visualizing it. So, in this case, you can see we have our little part in the lower right hand corner. Along that green side, we're placing an anchor plane. This would be similar to maybe placing this down on a table or a fixture on that side. And then we can measure from that table as a reference point. So our anchor plane is essentially that table, and we can measure how far the part is deflecting off of the table. So best fit is the second viewing option we have when reviewing our warpage analysis results. This is basically an unconstrained deflection in space. So our part's sitting out there and shrinking or deflecting around its centroid essentially. And there's no reference point. However, there are some tricks that we can use that will make this useful over the anchor plane in certain situations. And that might be where we would specify a certain number of reference points. Maybe the elements or points around those bosses, we could do a best fit around those and measure the out of round, for example. The next slide will show us some tricks. So you'll probably use anchor planes for most of your applications, and you'd investigate each region of the part. So you'd investigate maybe the right side of this box with one anchor plane, the left with another, and maybe the bottom with a third. But there are cases where the best fit method is a better alternative to setting up an anchor plane. Some of these situations might be for ideal or complex geometries. It's also useful for circular or cylindrical parts, like we kind of mentioned previously on our boss. So some tips here on this particular part is that we can see the default best fit in the upper right corner. It's just, there's no reference at all. It's just floating in space. This is really hard to interpret or interpret back to our real life results that we're seeing and measuring. So what we can do is a best fit around the bottom edge of that part, and it'll show us how that bottom edge, how flat it is. That's going to be slightly better on this part, but second best, you could always put an anchor plane on there. You could put an anchor plane in each corner of the part and see how it tips. It all depends on how you're going to really visualize this in reality and measure this in reality. because we want to use a similar measuring technique so our results align. You can get up to 4 results when running the warpage analysis. They are the warpage indicator all effects. You get one for differential cooling, one for differential shrinkage, and one for orientation effects. Now these last 3 results will always be available for dual domain by default. However, for 3D, remember you have to disable that aggregation option in your advanced tab, or else you will not get these last 3 results. So, when we were looking at some of the plots before for the anchor plane and the best fit, you're probably wondering where these red, green, and yellow areas came from. Well, they're based off the nominal maximum deflection value that you specify in that tool's menu. Anything shown in green means that your out-of-plane deflections are less than 80% of that value you specified. If it's yellow, it's between 80% and 120% of that value. So you might want to keep an eye on these areas. Red means that those deflections are greater than 120%. So it's definitely beyond your tolerance, and you likely need to take corrective actions or measures to satisfy your modeling and design requirements. You can customize your warp results as well. To do this, you just have to click on the result itself and then right-click to access the context menu and select Properties. From there, you have a few menu items or options where you can adjust how this is shown. For example, you can change the scale factor. That will allow you to magnify what the deflection looks like so you can get a better visual representation of what could be going on there. It doesn't alter the results, it just alters how you're seeing it. Okay, so let's say you've reviewed your results using some of the anchor planes and best fit techniques I showed you in previous slides. And maybe you're not quite within your tolerance. So we need to find how we can fix this. Now, these 3 contributors to warp, the differential cooling, differential shrinkage, and orientation effects, basically add up to give us our all effects plot. So, this simple technique can help us find what the main contributor is. So what I'll typically do is tile my results, and then I'll show my all effects in one corner, my differential cooling in another, differential shrinkage in another, and then my orientation effects. That allows me to compare each component to the overall deflection and see which one has the most impact on it. In this case, you can see the differential shrinkage is the main contributor for this part. So from here, I know I need to focus on things that'll help me reduce the differential shrinkage in my part, and that'll increase the likelihood of me fixing my issue here. When you're interpreting your warpage results, you really want to focus on the red and yellow regions, because the red ones are definitely out of tolerance and the yellow ones are very close. And then investigate ways to reduce the warpage in these areas. Again, this may take multiple anchor planes or multiple techniques to analyze each section of your part. You can also use the Results Advisor to examine the model and obtain design advice. So, I showed you before we use that tile technique. However, you can come in here and use the Design Advisor as well, and it'll tell you some information also. You see our all effects are red in this case, and if we look at our 3 individual components, we can see that the orientation effects are the problem on this one. Now, some things to keep in mind when you're reducing your warp. Your aim should be to reduce your warpage so it's within your design tolerances. Hopefully these tolerances are specified up front so you know where you need to be with them. It's generally not practical or even possible to reduce warpage to 0. This is a common trap that a lot of users fall into, and it's a great way to waste your time. So don't waste your time. How to reduce warp. First, you want to take measures to reduce the effect of the dominant warpage contributor, like we covered before. Is it differential cooling? Is it differential shrinkage? Or is it orientation effects? Each one of these components could have a different solution. So, target the one that is the main contributor and tackle that one first. Use the analysis results to help determine how to reduce the warp. adjust your processing conditions, add features to make the part more rigid, or even change the material. This is all stuff that you can do in the simulation before you get to the shop floor and it gets more expensive. So in summary, warpage trends can vary widely with specific combinations of your material, part geometry, processing conditions, and even mold construction. All of us can have different constraints in each one of these compartments, so there's not going to be one solution. That's why we can use the software and an iterative process to see what will work for us and our constraints. The mesh aggregation option will reduce both analysis time and accuracy in 3D, true or false. Using anchor planes is always better than using best fit when visualizing your warp results, true or false. If you're reviewing your warp plot, what do the green areas on the part represent? Your goal should be to always try and reduce your warpage values to 0, true or false. Now that you've had the opportunity to view this presentation, please try the following exercises to better sharpen your skills. For additional information on how to access these exercises, please refer to the introduction video. Thank you.